Magnetic fields, part 1. Consider a square and a circle. I promise this is going somewhere. You know that the square is bigger, but how much bigger? We'll consider side length A, and that's the diameter of the circle. That's twice the radius. Let's take a look at perimeter. You know the equation for perimeter. The circle, as shown here, has less than 80% the perimeter of the square. How do their areas compare? Well, again, with the equation for area, we know it's the same percentage, less than 80%. Consider not just a circle and a square, but how about a sphere and a cube? We'll take a look at surface area. Oh, it turns out now that the sphere has just over half the surface area of the cube, and the volume they're related by the same percentage. Again, I promise this is going somewhere. It's going to be current traveling in that circular loop, traveling in that square loop, and that's what they call it. Sounds funny, but a square loop of current. Which one of these will have a stronger magnetic field at the center? We can use the right-hand rule to tell us the direction of the magnetic field. Go ahead, use your thumb, put your thumb to the left, and you will have a magnetic field at the center of these two loops out of the plane of the page. To calculate its magnitude, we will use the Biot-Savart Law, which, I hope no one minds me, it's a very funny looking law. First of all, we notice that it gives a small piece of the magnetic field for each small piece of wire. We can trace the small piece of wire all the way around. Next, we notice this part of the law, which is very funny. We have a small little piece of wire, dl, the cross product with a unit vector. Basically, what this part of the law does is it tells you the direction. You know how to find direction using the cross product. Basically, this part of the law, it's not all it does, but it gives us the right-hand rule, which we already saw. It's also an inverse square law, but sometimes I'm not the only one who thinks it's kind of funny looking, because you will see it written like this, where r is no longer a unit vector, but a vector, and then it's an inverse cubed law if you write it like that. But we will write it like this and solve for the magnetic field at the center of the circular loop, which is, thankfully, it's pretty easy. Mu naught, the permeability of free space, is a constant. Current is a constant. Pi and r are constants, and we'll integrate the length, which is 2 pi r, and there we have the strength of the magnetic field at the center of that loop. Next, let's do that for a square loop, because this is more difficult. It gives us some practice with the Biot-Savart Law, and I thank this YouTuber for showing me how it's done. It starts with the fact that the derivative of tan theta is secant squared theta, and if you don't believe me, here's a quick and dirty derivation of that. Let's use it. But first, we have 4 different segments of wire. We'll multiply by 4 later, zooming in on this one segment, and there it is, a small little chunk of wire, and there we have an angle theta and some dimensions. With the cross product, you might be expecting a sine function, but look at how we're measuring theta. That gives us a cosine function there. Don't worry about complementary angles, just think about the perpendicular component is what the cross product is all about. Next, speaking of the cosine, we can use it to redefine r and square it and substitute in, because we want thetas. We'll be integrating d theta, so that means dx is a problem. Let us take a look at the tangent. X over a over 2, rearrange that, and you guessed it, differentiate. Dx is, what was the derivative of tan theta? Oh yeah, secant squared theta. That did come in handy. We can substitute that in. It's time to simplify, and it is time to integrate. 45 degrees to negative 45 degrees with the sine function, with 1 over the square root of 2 times 4 different line segments. Rearrange one last time, and we are done. Hey, look at that. This time the circle had the circle wins. The circle had a stronger magnetic field at its center. The square had only 90% of the magnetic field of the circular loop of current. The square may have been longer, but the circle was closer to the center. This was, however, just a warm-up. We'll take a look at more magnetic fields and more equations for magnetic fields in part 2.